SwayamPrabha. Digital India. Educated India.
So, hello and welcome back to one more lecture on Introduction to Soft Matter. So, last time we were discussing this particular example and that I had left it for you to solve. So, this was example 3 and the question was what will be, how many different Deborah numbers can you identify in this particular case. So, obviously now that we have seen that the relaxation time scale is already provided to you. So, the question finally boils down to figuring out what are the different time scales that you can associate with this particular problem. So, question is time scales, right? What are the different time scales? So, here at least one time scale you can borrow from the previous problem, right. So, time scale 1. So, just a second. Okay. So, time scale, let us say this is a one time scale, can still be given by 1 by omega. But you can also form another time scale now, and that time scale this is essentially a shear rate or the inverse of a shear rate. So, this new time scale is another. So, you can use this to define another Deborah number, or in this case often when people use the second one, it essentially becomes a Weisenberg number. So, with that we are done with our examples on, or we are done with our introduction to time scales and Deborah number, which are the two very important, the first important concept with regards to soft materials or viscoelasticity. So, now what we will do is we will go back to the initial, we had already discussed this in one of the lectures. What is viscoelasticity? And we had said that viscoelasticity is the property of materials which involves aspects of two types of common natural responses, classical elasticity and classical fluid. So, classical elastic solid or the classical viscous fluid. This definition was taken from one of the textbooks that are part of the recommended texts for this class. So, obviously, now the next step before we try to understand viscoelasticity should be to try and understand what a classical elastic solid is and what a classical viscous fluid is, right. That should be the obvious next step. Now, another thing we are going to do here right now, and I had discussed this in one of the previous lectures also, that there is a certain continuum approach to understanding viscoelasticity, where we do not necessarily discuss or depend upon what is the molecular constitution of the material. We are going to define macroscopic tests, where information on the molecular aspects is not necessary. Obviously, if you have that insight, it gives you a better understanding of the material response. But even if that is not available to you, you can still define macroscopic tests which can help you understand how a classical elastic solid differs from a classical viscous fluid, and then we will see what a viscoelastic material is, okay, which you can probably guess. I mean, we have already discussed this, lies somewhere between the two, right. So, in the textbook by Weinberg and Rajagopal, they give 6 different tests or macroscopic tests that one can do, which helps elucidate the behavior of a classical elastic solid or a classical fluid or any continuum essentially. So, the first test is called a stress response test or a response to step stress. Another one is the release of stress. A third one is a strain control test or the response to a step strain, and we will discuss each of these in more detail in a moment, and effect of different histories. When we say effect of different histories, it implies that effect of the different histories of one of the imposed variables. Then energy dissipation in the material, and 6, effect of sinusoidal oscillations, okay. And these are all provided in the these are the 6 tests as per the book Mechanical Response of Polymers by Weinman and Rajagopal. So, we will start a new page here. So, now we want to discuss macroscopic tests. Okay. But before we get into it, we have understood that to compare the viscoelastic response, so to compare viscoelastic response to that of a classical elastic solid or B, the classical viscous fluid we have to account for time as an explicit variable. Okay. So, what do we mean by that? We mean that the relationship between stress and strain when it comes to a classical elastic solid or a classical viscous fluid, typically the constitutive relationship does not account for time explicitly, it is already there, and we will. So, to get there, let us just quickly introduce a couple of variables that we will be using quite a bit. So, let us introduce sigma, which we will be using for normal or shear stress, and epsilon, which is again going to be a normal or shear strain. So, we are going to assume that you have some understanding of what stress and strain are, but I am also going to make another note, which is, so in a bracket I will make a note that we know, if you are familiar with stress and strain, we know that stress and strain are tensors and that they have to be very rigorously defined in many cases. Okay. So, we are not going to do that at the moment. We are going to take a very simple undergraduate as you might have seen in the undergraduate classes, a very simple understanding of stress and strain we will assume at the very moment. Okay. So, we will neglect, so we know that stress and strain are, so we will overlook the fact that sigma comma epsilon are tensors and have to be rigorously defined. And we are going to do that because we currently do not require the tensorial notation so much, and we are just trying to get some initial intuitive understanding. So, we just going to treat it almost like as if it is a scalar quantity. We will come back in one of the later lectures. We will introduce stress and strain as tensors when we discuss constitutive equations. More formal discussion of constitutive equations, we will come to that. Also, what do we mean by strain? So, here we are still going to go by some of the very early intuitive ideas that we had built up about what stress is. For example, if you have a rod and then the rod is of n naught size, then when you apply a normal stress, then the rod increases in length and becomes L naught 1 plus epsilon as a response to this. Okay. So, we will stick to this definition. This definition only works for very small strains, and if you have strains that have very large values, then there are other ways of defining strain. But for the time being, for the most of this course, we are not going to require that, and so we will confine our attention to this. But I am just letting you know that this is not a complete description of, or rather what we are going to take is a very simplistic understanding of these quantities. Okay. Now, I just said in the previous just in a few moments ago that we have to account for time explicitly. Okay. So, what do we mean by that? So, when it comes to a solid material, you are already familiar with a very famous rule which is given as right. So, E here is a modulus quantity. So, here what we do is the strain or the stress or the vice versa. So, we can say that stress depends only on instantaneous strains and vice versa. So, when we write this, we already are assuming that history effects are not important, right, because the stress at any given point of time depends exactly on the strain at that time and not a value of strain in the past, and vice versa is also true. So, now that we have discussed this, let us come. So, we are going to break this idea and we are going to start introducing time more explicitly in our conversation. And when we do that, we are going to go back. So, I am just going to quickly refer back to the 6 tests that we had discussed, right. So, the 6 tests were okay. So, let us just keep to the first test, sorry, just a second. So, the step control test or the response to step stress and the release of stress. So, what do these things mean? Okay. So, let us discuss the first one, which is the stress control test. So, I am just going to insert a second. So, we are going to use this image here. So, in this test what we are asking is that we have applied. So, stress control test should automatically tell you that the variable, that is experimental variable, that is under your control is the stress. So, you are applying a known amount of stress, let us say sigma naught in this case, and then you are measuring strain as a response of the material, right. So, the first diagram is the input in a sense, and the second diagram to the bottom is the output. So, this is this curve, the first one, this curve is your step control test, belongs to your step control test. So, this is step stress. So, you have provided a known value of stress to the system, and then you are going to measure what the output is. What we see for a classical elastic solid, okay. So, so just a second here, okay. So, what we are going to discuss is, so this is okay. Let me. So, as I said, first we want to understand classical elastic solid. So, for the next few moments our discussion will be for a classical elastic solid. Okay. So, this diagram tells you what happens when you apply a stepped stress to your system. What you get for a classical elastic solid is that the moment you apply stress or a stress of sigma naught, your system will instantaneously register a strain of epsilon naught, and this strain holds for as long as you keep your stress to that value. Okay. So, here the inherent assumption is, okay. So, inherent assumption is that the response is much faster than the resolution of experiment. And that the effect is essentially instantaneous. So, here when you apply the stress units, the step test, you immediately your system registers an epsilon naught, and this immediate is really immediate in a sense that the experimental resolution is much bigger than the response time. So, any material you can understand would take some amount of time, but in the case of classical elastic solids, they are so small that a typical experiment would not register them, and what you would end up seeing is essentially an instantaneous response. Now, so for the moment, for the time that we are going to discuss the continuum mechanics problems, we are going to treat this response as really instantaneous. When it comes back to the problem of when we start looking at the molecular nature, we will see why this response is very fast, and we will also get some idea of how fast this response is. really, because it cannot be infinitely 0. It has to be a finite number. We will come back to that problem, but for the time being we will just consider this as instantaneous. Now, so this is the first test, and what it says is it just continues for as long as you keep it, right. So, as long as you hold the strain at that value, stress at that value, the stress, as long as you hold the stress at that value, the strain will also be held at that particular value. Now, our second test was the release of stress, right. Okay. So, we had seen that our the second test was the release of stress. So, what happens when you release the stress? That also I have already drawn, this diagram has already been drawn. So, it already shows you. So, this indicates here release of stress. Okay. So, basically you should imagine that we are doing the experiment and we are measuring the output, and here at T end we have released the stress, and the stress now goes back to a value of 0. What ends up happening is that your strain also goes back instantaneously to 0. Okay. So, this was your second test. So, this was in a sense. Now, the third test, just going back to this, the third test was the strain control test. So, in this test we change the input variable. So, we change the input variable, and now this bottom diagram becomes your input, and the top one. So, the strain is now the input, is the experimental condition, and then you are measuring stress. So, what happens for a classical elastic solid when you flip the experimental control? What do you think happens? Does not change, it is the same that remains, right. So, here, so if you make the experiment strain controlled, as opposed to stress controlled, the nature of the graphs does not change. Right. So, this in a sense becomes your third experiment. Okay. Let me take this off, and this is I will just make it more general. We will just say these are, we are discussing tests for a classical solid. So, we have discussed 3 important points. Okay. Now comes the fourth point, which is the effect of different histories. When we say effect of different histories, it implies how did you reach that value of stress, or how did you reach that value of strain, and if we change it, what happens, right. So, in this diagram we have already indicated a few things. So, this is one path in the top. So, let us call this path A. This is another path, path B, by which you are reaching sigma naught, and this is another path, path C, by which again you are reaching sigma naught, but its time histories are different in the 3 cases. So, what happens here the corresponding diagram is already drawn for you, and what you see is that if epsilon naught is reached by different time histories, sorry, if sigma naught is reached by different time histories, epsilon naught will also be reached by different time histories. So, what you see is, if epsilon naught is reached at did we have a time here? Let me quickly check. So, t dash. Okay. So, let us just say this time by which it is reaching sigma naught is this time called t dash. If epsilon naught is reached at sorry, let me just change this. This is sigma naught. If sigma naught is reached at time t dash by distinct stress histories, the same strain is reached at t dash and is independent of the rate of change of stress or how the value at t dash is reached. So, if you reach sigma naught by distinct strain stress histories, the same strain epsilon naught is going to be reached at t dash, and it is independent of how fast you are changing your stress to reach that, and it is also independent of how this particular path was taken. Right. So, this is a very important issue with classical elastic solids, and this is basically what helps you get. So, when you are doing an experiment, you are always doing a time history type of experiment, where you are taking one value and you are changing it with time, or you are achieving it at a certain time, and you are recording that time response of the material. But since sigma naught and its corresponding epsilon naught is independent of how you reach that value, hence this explicit variable t can be dropped. Okay. So, hence explicit variable t can be dropped. And thus, irrespective of who has done the experiments with what history, you will always end up reaching the same conclusion. If many people were doing the different experiments at different histories, all of the different people will still, if they plot sigma versus epsilon, they get the familiar straight line curve, where the slope is a function of the material itself. Okay. So, the slope gives you a material response. Okay. So, that is why we write this as sigma equal to E epsilon, where this is a modulus. You already know this, but this modulus is a material property. Sorry. So, just going back. So, these different strain histories, these are basically your fourth type of test. So, that leaves us with two tests still, that is energy dissipation and effect of sinusoidal oscillations. So, with regards to energy dissipation, we have seen that, just to go back, that when you apply a known amount of stress, the system goes to a certain amount, registers a certain strain, and this strain holds for as long as you want, infinite. That is just our simplification. Obviously, that cannot be true, but for the theoretical or from a theoretical perspective, the idea of a classical elastic solid is that it can hold that amount of strain for an infinite amount of time. And obviously, as you release the stress, this strain also comes back. So, whatever energy that you put in or the work done is recovered when you release the strain, release the stress. So, the system stores energy for the time that you want, and then the moment you leave it, the energy is recoverable. Okay. So, when it comes to energy dissipation, all energy, so the system, just a second. So, the system, which in this case is the classical elastic solid, stores the energy, the applied energy, and this energy can be recovered fully. So, that we have one more. So, this was the fifth test, and we have the final one, which is effect of sinusoidal oscillations. So, in sinusoidal oscillations, let us say your input is sigma equal to sigma naught sine of omega t. So, you are deliberately applying a sinusoidal oscillation in this case, and then you are measuring the output, right. So, what is your output going to be? We have already seen that stress and strain are proportional. So, this is going to be some other epsilon naught again sine of omega t. So, here please note that there is no phase difference between the two. So, between the input and the output, they are always in phase, and amplitude does not depend on omega. As you have already determined that sigma equal to E, there is a modulus times an epsilon. Okay. So, today what we did in our today's lecture is that we started looking at the continuum mechanics we started taking a continuum mechanics approach to understanding viscoelasticity, and we have taken the first step in that direction by trying to figure out what are the requisite tests for us to understand, and we found that there are 6 different tests, and these 6 different tests that are suggested in the textbook we have applied it to a classical elastic solid, and we have seen what the classical elastic solid's response will be. And in the next class, we will look at a classical viscous fluid.